In this worksheet, we're going to do a couple of examples of electrophilic aromatic substitution reactions, focusing specifically on the mechanism. So in these steps, I'm giving you kind of the general guide for drawing an electrophilic aromatic substitution mechanism. And we're going to start by writing this generic mechanism for the reaction using E plus as the electrophile. The first step of this reaction, any one of the double bonds in the benzene ring is going to attack the electrophile. I'm going to attack with this bond right here because I have the hydrogen drawn in for the purposes of the mechanism. I do want to make sure that it's clear that there are the correct number of hydrogen atoms on this benzene ring. I'm just choosing to show this particular one. So the double bond is going to attack the electrophile, and that is going to give us a structure that looks, initially it looks like this. We've lost this double bond because we're using it to form a bond to an electrophile. The hydrogen atom is still present. The electrophile has been attached to the ring, and then the other carbon that was part of the double bond now has a positive charge on it. In terms of where the electrophile can go on the carbons of the double bond, it can go to either one of these positions, but I'm choosing to focus again on this carbon. That's why I drew this hydrogen right here, and that's where I would like to put the electrophile. Now we're going to, this particular molecule has resonance structure, so now we're going to draw the resonance structures for this molecule. The only way that this reaction can take place is if this intermediate is stabilized by resonance. So for the first resonance structure, we're showing that double bond that I drew the arrow to. That double bond is being delocalized a little over to the right. And then we're going to do the same thing with the other double bond, delocalize that one as well. These resonance structures, the set of resonance structures, are referred to as the sigma complex for this molecule. So we'll put some brackets around it because these are the resonance structures. And now, answering the question, is the sigma complex aromatic? The sigma complex is not aromatic. It is violating right there the structural criteria for aromaticity because it has that sp3 hybrid carbon. So we'll say no because there is an sp3 carbon in the ring at this moment. In the last step of the reaction, then we are going to abstract the hydrogen and put this molecule back to being aromatic. Depending on the actual reaction, the actual electrophile, there's some sort of base that's involved in this abstraction process. The base will vary as the electrophile varies. The base is going to grab the hydrogen atom, the one that I've drawn, the hydrogen atom that is on the same carbon as the electrophile. The carbon-hydrogen electrons are going to go into the ring to reform that third double bond and return aromaticity. So it's going to look like this with the electrophile left behind. And the molecule is now aromatic. Let's look at a couple of specific examples. So question number 2, draw the mechanism for the chlorination of benzene. We can use this as our guide. We're going to start with a benzene molecule, and our electrophile is Cl+. And we can pick any one of the double bonds that we want. I'll just pick the one that's closest and put that chlorine on either one of the two carbon atoms of the double bond. So we're going to get this right there. This is the first of our resonance structures. So now I'm going to draw the two resonance structures. We do this by just shifting those double bonds one at a time around the ring, which delocalizes that positive charge. And we've got one more to go, like that. And after you've drawn a few of these sigma complexes, you just really don't want to draw them anymore, so you just kind of start leaving them out. And then in our last step, we're going to do the hydrogen abstraction. We're specifically going to be abstracting the hydrogen that is on the same carbon as the chlorine electrophile. The base for this particular reaction is AlCl4-. AlCl4-. That is going to grab that hydrogen. Carbon-hydrogen electrons are going to come in to create the third double bond in the benzene ring. We can go ahead and just abbreviate the benzene ring at this point. And it's not standard to write the formation of the product that's formed when the base abstracts the hydrogen. So normally we're just going to leave that out. We've got one more mechanism to go. This is going to be Friedel-Crafts alkylation of benzene. We're using 1-chloropropane as our alkyl halide. So actually, I think I'm going to move this down. I'm going to start by drawing the 1-chloropropane. That's this molecule right here. Now, to get this molecule ready, to get the 1-chloropropane ready for this reaction, the chlorine is going to be removed from the molecule, and it's going to make a carbocation. That's going to be our electrophile, but because this is a primary carbocation, it's actually going to rearrange itself to form a secondary carbocation. This is the actual electrophile that we'll be using in this reaction, right there. And we're going to take a double bond. I'm going to use this one right here and form a bond to the benzene ring. That bond that I'm forming is going to be to either one of these 2 carbon atoms in the benzene ring. My choice, I'm going to put it up top like that, which means that I have a positive charge in this position. Now I want to draw, well, I don't really want to, but now I'm going to draw the sigma complexes, showing those electrons being delocalized around the ring, like that, and we have one more to go. And there they are. In the last step, we're going to abstract the hydrogen that is on the same carbon as our electrophile. The base that we're going to use is the same as the one that we used in the previous reaction, AlCl4-. The base is not always the same. Don't think that that's the case. We're going to grab that hydrogen and move those carbon-hydrogen electrons in to form a double bond. And there is the product. You got to be really careful with the Friedel-Crafts alkylation reaction with the rearrangement of the carbocation. It's one really tricky part of the problem. It's really easy to forget to do that, so make sure you're always paying attention to that.